Section D, Graphs of Exponential Functions.
Just like with rational functions, there are some general characteristics of graphs of exponential functions that help you understand how these functions operate. Look, here comes one now. It says, for an exponential function of the form y equals ab to the x, the y-intercept is represented by the coefficient a.
For example, the graphs of y equals 5 times 2 to the x, y equals 5 times 3 to the negative x, and y equals 5 times 0.45 to the x all cross the y-axis at 5. You've seen that many applications use the variable t for time. When this is the case, the y-intercept is the same as the starting value corresponding to a time of 0. Notice also that the graphs all have the general appearance of ski slopes that level off at the bottom. Some of them level off to the left and some level off to the right, but they all level off along the x-axis. In fact, the x-axis is an asymptote for these graphs in the same way that it can be used for an asymptote for a rational function.
Whether the graph levels off to the left or to the right depends on whether or not there's a negative in the exponent. If there is no negative sign, as in y equals 5 times 2 to the x, or y equals 5 times 0.45 to the x, the rule is this. When the base is bigger than 1, the left side of the x-axis is the asymptote. When the base is less than 1, the right side of the x-axis is the asymptote. Tracing the graph from left to right, the curve is sloping downhill when the base is less than 1 and uphill when it's greater than 1. This is what happens for y equals 5 times 2 to the x and y equals 5 times 0.45 to the x. If there is a negative sign in the exponent, the rule is reversed. Then, for y equals 5 times 3 to the negative x, the base 3 is bigger than 1, so we would normally expect the graph to go uphill from left to right, but the negative sign reverses this. The curve goes downhill from left to right, and that means the right side of the x-axis is the asymptote.
Different exponential functions have very similar graphs, varying mainly in their steepness and whether they slant uphill or downhill. In fact, there are pairs of graphs that are mirror images of each other.
For example, y equals 2 to the x and y equals 2 to the negative x are just mirror images of each other. Remember that 2 to the negative x is the same thing as 1/2 to the x. So y equals 2 to the x and y equals 1/2 to the x are also mirror images.
Here's one final point about graphs. Let's compare several examples with different choices for the base.
Compare these graphs. Y equals 0.2 to the x, y equals 0.5 to the x, y equals 0.9 to the x, y equals 1.1 to the x, y equals 2 to the x, and y equals 5 to the x. There is a clear pattern showing the effect of different choices of the base. Keep this image in mind because it helps you visualize how different choices of the base should compare. Notice how all the curves have roughly the same shape, differing only in steepness. Check out the point where they all cross at 1 on the y-axis. It's a good way to compare the steepness of the different curves. This idea of looking at the slope where the exponential function crosses the y-axis will come in handy with what we're covering next.